Welcome back to the show, everyone. Today we'll be taking a deep dive into some research you sent in on linear regression and gradient descent.
Two really fascinating areas in the world of machine learning.
Absolutely. And, I think from what I saw in your request, you're really hoping to get like a solid understanding of these concepts
Yeah,
without getting, too bogged down in all the jargon and the complexity.
right.
So we're going to try to unpack some of the key ideas from your research in a way that's approachable and fun, but also gives you that deeper understanding that you're
Yeah.
looking for. So get ready for some aha moments.
It's kind of like giving machines that sixth sense, right? Allowing them to see patterns and relationships that we might not immediately
Oh, that's a good way to put it.
pick up on.
Yeah, like revealing the hidden connections in the data.
Exactly.
Okay, so let's start with the basics. Linear regression. Your research points out that it's all about finding relationships
hmm
between features and a label, right?
Yeah, essentially, we're trying to predict that label based on what we know about those features.
Okay, so can you give us a concrete example to kind of illustrate this?
Sure. Um, Imagine we're trying to predict a car's fuel efficiency, so like miles per gallon,
Okay.
based on its weight.
Got it. So weight is our feature,
hmm
and MPG is the label we're trying to.
Exactly. And we'd probably expect that a heavier car would generally have lower MPG,
Yeah.
right?
Yeah, makes sense.
So there's a relationship there that we're trying to capture.
Right, but how do we actually quantify that relationship? I noticed in your notes you had mentioned the linear equation.
Yeah, absolutely.
Okay.
So the equation is basically our model of that relationship. Uh, it takes the form of y prime equals b plus w1x1.
Okay, break that down for us.
Sure. So y prime is our predicted MPG, b is what we call the bias. W1 is the weight assigned to our feature, and x1 is the feature itself, in this case, the car's weight.
Got it. So the bias is like our starting point, and the weight tells us how much the MPG changes for every pound of weight.
Exactly. And that weight would likely be negative in this case, since heavier cars tend to have lower MPG.
Okay, that makes sense. But what if we want to consider other factors that might affect fuel efficiency, not just the weight?
That's where things get really interesting. We can actually add more features to our model to make our predictions even more accurate.
Okay, so what other features could we include?
Well, we could think about engine size, the number of cylinders, even something like the car's aerodynamic design.
Oh, yeah, that could definitely play a role.
Exactly. Each of those features would get its own weight in our equation, allowing the model to capture more of the nuances of fuel efficiency.
So the more relevant features we include, the more refined our model becomes.
Just,
But
yeah,
how do we know if our predictions are any good? We need some way to measure how accurate they are, right?
you're absolutely right. And that's where the concept of loss comes in.
Loss. Yeah.
Yeah, it's basically a measure of how much our predictions deviate from the real MPG values we observe in actual cars.
Oh, I see. So it's like a gauge of how off our predictions are.
Exactly, and our goal is to minimize that loss.
Makes sense. Now, I noticed in your research you mentioned different types of loss, MAE and MSE.
hmm
What's the difference between those, and why would we choose one over the other?
Yeah, that's a great question. So both of them measure the difference between predicted and actual values, but with a slightly different emphasis.
Okay.
MAE, which stands for mean absolute error, looks at the pure magnitude of the difference, just how far off we are.
Okay.
Whereas MSE, or mean squared error, actually squares those differences,
Mm-hmm.
which means that bigger errors are penalized much more heavily.
Oh, interesting. So MSE would be more sensitive to outliers then.
You got it. If we had a data set with a few cars that had unusually high or low MPG for their weight, MSE would react more strongly to those.
Right. But wouldn't that be a disadvantage sometimes? I mean, if those outliers are like data errors or anomalies?
That's a great point. And that's exactly why the choice between MAE and MSE depends on the specific data set and how we want to handle those outliers.
Yeah. It's like deciding whether those outliers deserve a parking ticket or a full-blown speeding fine.
I like that analogy.
Okay, so we've got this way to quantify how good our model is, but the big question is, how do we actually improve it? How do we make those predictions more accurate?
Well, that's where gradient descent comes in.
Hmm.
It's an algorithm that helps us find the best weights and biases for our model.
Okay, so it's like giving our model a set of instructions to get better.
Exactly. Gradient descent guides our model on its learning journey.
I like that, a learning journey, but how does it actually work?
Well, it's an iterative process. So we start with some random values for our weight and bias.
Uh-huh.
And then we use our model to predict the MPG for each car in our data set.
Okay.
And we calculate the loss using MSE in this case.
So we see how far off our predictions are.
Right. And then the gradient tells us which direction to adjust our weight and bias to reduce that loss.
Okay, so it's like we're nudging those values ever so slightly to get closer to the right answer.
Exactly. We make small adjustments, then we recalculate the loss. And we repeat this process over and over
Uh-huh.
until the loss is as low as we can get it.
So it's like we're taking tiny steps downhill, always aiming for the lowest point.
That's a great way to visualize it.
So with each step, our model gets a little bit better at predicting fuel efficiency.
Precisely.
But how do we know when to stop? You mentioned something called a loss curve earlier.
Yeah, the loss curve is a visual representation of this learning process.
Okay.
It plots the loss against the number of iterations.
So we can see how the loss decreases as the model learns.
Exactly. Imagine a graph where the y-axis represents the loss and the x-axis represents the iteration number.
Got it.
At the beginning, the loss is high, so the curve starts high up on the axis.
And as the model learns, the curve should start to descend.
Precisely. It should ideally descend smoothly, getting flatter and flatter as we approach the optimal set of parameters.
So a steep drop means the model is learning quickly,
Mm-hmm.
and a flat line means we're getting close to the best possible solution.
Exactly. The loss curve gives us a way to monitor the progress of our model and see if it's converging towards a good solution.
That's fascinating. So we've been talking about tweaking the weight and bias to improve our model,
Yeah.
but are there other things we can control that might affect this whole learning process?
Absolutely. And that brings us to the concept of hyperparameters.
Hyperparameters. Okay, I think we'll save that for part 2 of our deep dive.
Sounds good. So we left off talking about hyperparameters.
Right, hyperparameters.
And we can kind of think about them as the knobs and levers that we as machine learning engineers get to adjust. They control how our model learns, so they don't directly affect the model's parameters like the weights and biases we were talking about.
Right.
But they kind of set the stage for how those parameters are learned.
Got it. So we're not directly manipulating the model's calculations,
Mm-hmm.
but we're kind of setting the rules of the game for how it learns.
Exactly. It's like we're the coach and the model is the athlete.
Okay, I like that analogy.
We can't control every single movement the athlete makes, but we can definitely influence how they practice.
Right, so what are some of these key hyperparameters that we get to play with?
Well, 3 of the most impactful ones are learning rate, batch size, and epochs.
Those sound familiar. We talked about learning rate a bit earlier. Remember those tiny steps the model takes during gradient descent?
Exactly. The learning rate controls the size of those steps. So choosing the right learning rate is super important.
Why is that?
Well, if the learning rate is too small, our model is going to take forever to converge. It's like taking baby steps down that lost landscape.
Okay, so it'll eventually get there, but it's going to be slow.
Right, exactly. But on the other hand, if the learning rate is too large, the model might overshoot the optimal values and bounce around chaotically and never actually settle down.
So it's like trying to take giant leaps down a hill. You might miss the target completely.
Exactly. So we need to find that sweet spot, that Goldilocks learning rate that's just right.
Not too hot, not too cold. So how do we know if our learning rate is just right? Can we use the loss curve for that?
Yes, absolutely. The loss curve can be super helpful here.
Okay.
So if the learning rate is well chosen, the loss curve will show a nice, smooth descent,
Okay.
like a gentle slope leading down to a valley. But if the learning rate is too small, that descent is going to be really slow and gradual.
So the curve would be really flat.
Right. And if it's too large, the loss curve might jump up and down erratically.
Oh, so it's like the model is taking those giant leaps and missing the mark.
Exactly. It's a sign that the model is struggling to converge.
Wow. So we can learn so much just from looking at the shape of that curve.
For sure.
Okay, so learning rate makes sense. Let's talk about batch size now. I remember you mentioning that when we were discussing stochastic gradient descent.
Right. So batch size determines how much data our model digests before updating its parameters.
Okay, can you elaborate on that?
Sure. So imagine our model is like an athlete training for a competition.
Okay, I like where this is going.
And the batch size is like how often we give them feedback during practice.
Got it.
So at one extreme, we could give feedback after every single rep. That would be like stochastic gradient descent, or SGD, where the batch size is just one data point.
So every tiny bit of data leads to an adjustment.
Exactly. But that can also make the learning process quite noisy.
How so?
Well, since each update is based on just a single data point, the model's paths can be kind of erratic, jumping up and down as it tries to find the right direction.
It's like the athlete constantly changing their technique based on just one rep.
Right, they might miss the bigger picture.
Okay. That makes sense. So SGD is fast, but maybe a little bit unreliable.
Right. It can be unstable.
What about the other extreme then?
The other extreme would be full batch gradient descent,
Okay.
where we use the entire training data set before making any adjustments.
Oh, wow. So it's like letting the athlete do their whole routine before giving them any feedback?
Exactly. It's very thorough, but it can also be really slow.
Yeah, especially if we have a massive data set. But it would be very stable though, right?
Yeah, exactly.
I don't know.
Each update is based on a comprehensive view of the data, so the steps are much more deliberate.
Okay, so it's like getting feedback from a whole panel of expert judges.
Exactly. You're more likely to get a balanced and accurate assessment that way.
So we have these two extremes, then fast but noisy versus slow but stable. But you mentioned something called mini batch SGD earlier.
Right. Mini batch SGD is like a compromise between those two extremes.
Okay.
We choose a batch size that's somewhere in between one data point and the entire data set.
So it's like giving feedback after every set of reps or something.
Exactly. And that seems to work really well in practice.
So it's a balance between efficiency and stability.
Right. And here's the really interesting part. That bit of noise we saw in SGD can actually be a good thing sometimes.
Really? Why is that?
Well, it can help our model escape local minima.
A local minima.
Yeah, those are like little valleys in the loss landscape that aren't actually the lowest point.
Oh, I see. So we don't want our model to get stuck in a valley when there might be a deeper valley somewhere else.
Exactly. And that little bit of randomness in SGD can help the model jump out of those valleys.
So a little bit of chaos can actually lead to a better solution.
Sometimes, yes, it's like allowing the athlete to experiment a little bit.
I see. So mini batch SGD gives us that balance between exploration and stability.
Exactly.
This is fascinating. So the choice of batch size isn't just about speed. It's about finding that sweet spot between speed, stability, and exploration.
It is, and it often depends on the specific problem we're trying to solve and the characteristics of our data.
Okay, that makes sense. Now we've talked about learning rate. We've talked about batch size.
Yep.
What about epochs?
Epochs. So epochs tell us how many times our model goes through the entire training data set.
Okay, so it's like practicing the whole routine multiple times.
Exactly. And just like an athlete gets better with each practice session.
Our model gets better with each epoch.
Right. One epoch means the model has seen every single data point in the training set.
Got it. And that gives it a chance to learn from all the information we're giving it.
Precisely.
So the idea is that seeing the data multiple times helps the model really learn the patterns.
Exactly. It's like, reading a book multiple times. You pick up on new things each time you read it. Right.
Definitely, you start to see the connections and the nuances that you might have missed on the first pass.
Right. And it's the same with our model. The more times it sees the data, the better it's going to understand those underlying relationships.
Okay, that makes sense. But then why not just set the number of epochs to like a really high number and let it run forever?
Well, there's a trade-off there. We have to be careful not to overfit our model.
Overfit? What does that mean?
So overfitting is when our model learns the training data too well.
Too well? How can that be a bad thing?
Well, imagine you're studying for a test and you memorize all the answers. You might get a perfect score on that specific test. But you probably won't do so well if you're given a different test with different questions.
Oh, I see, because you haven't really learned the material. You've just memorized the answers to that one particular test.
Exactly. And it's the same with our model. If we train it for too many epochs, it might start to memorize the training data instead of learning the general patterns.
So it'll perform really well on the data it's already seen, but it won't be able to generalize to new data.
Right. And that's what we call overfitting.
Okay, so how do we prevent overfitting then? How do we know when to stop training?
Well, there are a few techniques we can use. One common one is to split our data into a training set and a validation set.
Oh, okay. So we're holding back some of the data.
Exactly. We use the training set to train the model, like we've been talking about, and then we use the validation set to test how well the model generalizes to new unseen data.
So it's like a pop quiz to see if the model has really learned something.
Exactly. And as we train for more epochs, we keep an eye on the model's performance on both the training set and the validation set. If the performance on the training set keeps improving, but the performance on the validation set starts to decline, that's a sign that we're starting to overfit.
So it's like the model is getting really good at answering the practice questions, but it's starting to struggle with the real test.
Right. It's becoming too specialized to the training data.
Got it. So finding the right number of epochs is about finding that balance.
Exactly. We want to train for long enough to achieve good performance, but not so long that we start to overfit.
It's like finding that sweet spot between practice and game time for our athlete.
Exactly.
This has been such an insightful deep dive. I feel like I've learned so much about linear regression, gradient descent, and the whole process of training machine learning models.
Me too. That's really fascinating stuff.
It is, and I think the key takeaway is that machine learning isn't magic.
Hmm.
It's a combination of clever algorithms, data-driven insights, and human ingenuity.
I agree. It's all about understanding the data, choosing the right tools, and carefully guiding the learning process.
Exactly, and I think this deep dive has given our listeners a great foundation for understanding how machines can learn from data and how we can make those machines smarter.
Definitely, it's a rapidly evolving field, so there's always more to learn and explore.
Absolutely. Well, on that note, I think we'll wrap up this deep dive. Thanks for joining us on this fascinating journey, and until next time, keep those brains engaged and those curiosity fires burning.